Welcome, everyone. Let's just jump right into today's explainer. We are going on a really fascinating journey into the advanced side of LangGraph. We're moving way beyond those basic language model queries and figuring out how to build intelligent systems that can actually take real-world actions and, crucially, remember their past interactions. We're going to break down two incredibly powerful concepts today: tool calling and reducers. If you've ever been working with LLMs and just felt like you hit a brick wall when trying to build practical, dynamic applications, well, you are in the exact right place.
To kick things off, we really need to ask a foundational question. How exactly do large language models interact with the outside world? Because out of the box, an LLM is basically trapped in a digital box. It's confined completely to the static data it was trained on. Sure, it can write a beautiful poem or debug a snippet of code for you, but it is totally isolated from real-time data or external systems.
So, here is our roadmap for today. 1. The LLM limitation. 2. Intro to tool calling. 3. Binding tools to LLMs. 4. The missing message problem. And 5. Fixing memory with reducers.
Okay, Section 1, the LLM limitation, and those out-of-the-box boundaries.
Imagine you ask your AI a seemingly simple question. Something like, can you fetch the enrollment numbers from the PISA database? Or, please deposit $700 into Junaid's account. If you ask a standard model to do this, you're going to get a very polite but very useless apology. It'll just tell you, I am an AI, I cannot access real-world systems. Right? It doesn't have your database credentials, and it certainly isn't wired into a bank. It lacks those external connections. This is exactly the limitation we have to overcome if we want to build truly useful agents.
Moving on to Section 2, Intro to Tool Calling, or, as I like to think of it, giving the AI hands.
So, the crucial point here is defining what we actually mean by tool calling. In the LangGraph ecosystem, tool calling is empowering your LLM to interact with external systems. But here's the real secret sauce. The LLM doesn't actually execute the code. It doesn't query the database itself. Instead, it intelligently selects which custom function to use, and then it extracts the exact arguments needed for that function, all based entirely on the natural language prompt you gave it. Think of it like a business. This brilliantly illustrates the separation of responsibilities. The LLM is the manager. You give it a natural language request, and the manager looks at its available tools and decides, okay, I need to use the deposit function for this. But the manager doesn't get its hands dirty. It hands those instructions over to the worker, which in this case is your LangGraph or Python environment. The Python environment is what actually runs the code, connects to the API, and does the heavy lifting.
Let's look at what this actually looks like under the hood. For a basic LLM output, you just get empty content, just that standard apology we saw a minute ago. But with tool calling enabled, the output completely transforms. Instead of a text response, the LLM returns a structured JSON object. It explicitly says, call the function named deposit money, and here are the arguments. Name is Junaid, amount is 700. It is literally translated messy human language into strict, actionable machine parameters. It's pretty amazing.
Section 3. Binding tools to LLMs. Let's introduce those tools.
So how do we actually wire this up? This is the exact step-by-step flow using LangGraph's bind tools method. Step 1. The user sends their natural language query. Step 2. The model looks at the tools you've bound to it. But wait, how does it know what a tool does? Well, it reads the Python docstrings. Finally, Step 3. Once it understands the tools, it returns the specific function name and those extracted arguments. You are essentially linking a Python function directly into the LLM's brain and decision-making process.
I absolutely cannot overstate the importance of this next part. Your Python docstrings are no longer just optional little notes for other developers. They are the literal instruction manual for your AI. When you write a function for it to deposit money, your docstring must clearly define its purpose. It has to specify that the argument name means the account holder's name and that amount is an integer representing the dollars to be transferred. If your docstrings are vague, the LLM is flying blind, and it will fail to trigger the tool correctly. Okay, so we've got our tools bound, the LLM returns the right arguments, total success, right? Well, actually not quite.
Which brings us to Section 4, the missing message problem. The architectural flaw. When you run this newly minted graph, you're going to immediately notice something terrifying. You send the human message, the AI processes it, the tool gets called, but wait, where did the human's message go? When you check the state history, the original prompt is completely vanished from memory.
This shows the exact problem with using a standard dictionary setup in Python for your state. In a basic state dictionary, when the graph runs and the AI generates its new response, it takes that AI message and just overwrites the old state. The dictionary key gets updated and boom, your human message is totally gone. Your AI now has complete amnesia. It knows it just called a deposit function, but has completely forgotten why it did it or who asked for it in the first place. And let's be real, you absolutely cannot have a conversational agent if it forgets the conversation every single turn.
Section 5. Fixing memory. Enter LangGraph reducers.
The crucial fix here is a concept called reducers, and specifically the add messages reducer in LangGraph. Instead of treating your state like a static variable that just constantly gets replaced, a reducer fundamentally changes that behavior. It takes the new message and appends it to a growing list. It concatenates the history.
Let's look at what the fixed state looks like. Because we're using the add messages reducer, we now have this beautiful chronological list. Message 1 is the human's original prompt, deposit $700 for Junaid. And message 2 safely coexists right below it, the AI's function call. Both messages have their own unique IDs, and the entire context is preserved. The amnesia bug is officially cured.
But here's the thing, appending state isn't just about keeping a chat log. It is a total game changer that unlocks incredible advanced features. This opens the door for human-in-the-loop workflows, where a human can literally pause the graph, read the history, and approve an action before the tool ever runs. It allows for time travel debugging, meaning you can rewind your agent to a previous state if something breaks. It gives your entire system massive fault tolerance and deep, deep context awareness.
So let's recap. We've taken our LLM out of its isolated little box, we've given it tools to actually interact with the real world, and we've secured its memory with reducers so it never loses context. You now have the exact blueprint for a truly interactive, stateful AI. So the only question left to ask is, with persistent memory and dynamic tools at your fingertips, what agent are you going to build next? Thank you so much for joining me on this explainer, and happy coding.